Are you all having a good day? Yeah? Yeah! Come on. Okay, so I'm Mark. In a former life, was a browser engineer. These days, I look after technical security for a company called Causally. And I'm sort of talking a little bit about my former life because it's one of these areas that I find fantastically interesting. How much of what we do day to day as security professionals comes from browsers. So, hands up, anybody got any ideas on things that you use day to day that came from the browser world? Throw things at me. Not literally. TLS? Anyone use TLS? Yeah, that was a browser thing, wasn't it? That was introduced by Netscape. JavaScript, so that's a browser thing, yeah. Oh, moving on from that, how about WASM? WASM's a runtime that came from browser stuff. Anyone got a bug bounty program? Where did bug bounty programs start? Yeah, browsers. What about type-safe and memory-safe systems languages? Rust was literally invented to build a browser. Yeah? How about sandboxing in consumer products? Browsers, right? So there's loads of stuff that we use every single day as security professionals. The foundation of lots of the technical parts of our discipline that came from the development of one family of products, right? And that's kind of interesting, isn't it? Or am I, way off here? Is it interesting? I think it's interesting. Do you think it's interesting? Okay. And all of these things didn't come at once, right? Browsers have been around for a long time, and if we're honest, they didn't start well. I'm not really good with clickers and stuff. I talk for too long. Well done. Scott, help. Oh, there we go. We're back. We're back in the room. Okay. They had a pretty inauspicious start. And, it's not surprising because think about what browsers do. Right? Imagine you're going to design a computer system and somebody comes to you with the requirements and says, I need you to help me secure this thing. I'm going to write it in C++. The input comes over the internet from untrusted sources. We've got loads of different contexts, right? Different things that aren't allowed to influence each other or read each other's data. Is that all right? Oh, by the way, the input data, it's going to be badly formed, and you've still got to deal with it, And we want it to, by design, be able to execute arbitrary code. And at what point here do you say, actually, no, that building this is just a really, really bad idea? Yeah, because you would, wouldn't you? If someone came to you with that and said, here's what I'm going to do, and you'd be like, no, just go home. And so it's not surprising when people had problems with early browsers. This is one of my favourite sentences on Wikipedia about the same origin policy in browsers. Do you all know what the same origin policy is? So the same origin policy is the thing that stops one website from being able to read or influence what's going on another site. Okay, it's sort of the foundation of the web security model. The concept of the same origin policy was introduced by Netscape Navigator version 2.02 in 1995. Shortly after the introduction of JavaScript in Netscape 2. So there's a horror story in two sentences, right? They built a thing and then they built the security model, right? And this tells us something really interesting about browsers. They've built these things that are hugely complex. They're runtimes. They're the operating system for modern distributed applications, essentially. And they built them basically by trial and error. So what I'm talking about now is how can we learn from this, right? Because we all work in messy environments where nothing's perfect to start with. What can we learn about how they've designed and built these things that helps us in our everyday jobs? So that's what this talks about. Long introduction, but that's basically what I'm talking about. And I'm talking about it from the perspective of a former browser engineer. I worked on one of these two things. And if you've used either, you've used my stuff. But they had very different approaches to security in the last 10 years, right? Actually, last 15 years. Because when Chromium came along, the Chromium project first started, it was brand new. It was a new code base, it was a new product, it had its own set of new users that weren't used to doing things in a particular way, and there was a whole new add-on ecosystem, right? Firefox, on the other hand, had the problem that there was an old code base. Some of that code had been in there since Netscape Navigator. Actually, no, some of the code base came from NCSO Mosaic, right? So it's an old code base. Been around for donkey's years. Loads of people that loved it. In particular, they loved the add-ons that they used, and they were going to be really upset if you broke them. And there was a large existing ecosystem where loads of people were heavily invested, right? And so when Chrome came along, it could do stuff that the other browsers couldn't, right? And this was true of Safari and Internet Explorer at the time as well. So they could do things like sandbox processes. They could separate the processes. They could have different origins isolating their stuff within a particular context. And so Mozilla, when they looked at this, they thought, well, we can't do a load of that stuff. What can we do instead that gives users a similar level of safety, but without these head starts? And over time, they caught up on a few of them. But the big thing that Mozilla did, and this is a brilliant thing, and I will go on about this as long as you like at another time, they literally invented a systems language to help them safely do a load of these things. We'll get to this in a bit more detail in a moment. But Rust is a thing that they did. They said, okay, if we build things such that we can eliminate a class of security bugs, we can provide equivalent safety without some of the stuff that the competitors are able to do. And then they caught up on the other stuff as well. As an aside, Chromium has now just started accepting Rust code in the Chromium tree, which is, good news for everybody. Google are picking up quite hard on Rust at the moment, which is good. Okay. So let's talk really briefly about sandboxes. Who's heard of a sandbox before? Okay, so the short version here is the technology varies from platform to platform, but the idea basically is that you can use underlying operating system primitives to make sure that different things are restricted in what they can do. Okay, so you can restrict access to the file system, you can restrict access to the network, and you basically architect your product such that different parts of the product are allowed to do different things. Okay, so you might have a content process which is allowed to talk to the origin server and get stuff, and it can run things, but it isn't actually allowed direct access to the screen or to the WebGL driver or the audio subsystem or printers or things like that, right? And then you can also isolate the stuff underneath. But the technology isn't the whole story, right? So I can refresh my memory and go into detail on how a load of this stuff works. I've done a load of it on Linux before. But the key thing here is that you've got boundaries and that allow things to happen. And this is a really nice graphic that I stole from the Chromium documentation, which talks about this idea in security called the rule of two. Has anybody heard of this before? Yeah. Okay, so the rule of two basically says there are three things, right? There are unsafe, ill-defined inputs. There are unsafe implementation languages, like C and C++, for example, and then there are high-privilege things, right? And you can pick any two, right? If you pick three, you're doomed. Now, you'll notice that the middle of that Venn diagram there, well, that's where browsers live, okay? So you inherently need to do all three of those things. So how do you re-architect your thing so that you never end up with all three overlapping? Now, those of you here who know anything about me know that I like robots. What else do I like, people? Chickens. Okay, so I'm going to illustrate this with a chicken example. I've got some chickens at home. The problem with chickens is that they need to eat and drink, and also they get eaten. So you don't want your chickens to have unrestricted access to outside, because otherwise the foxes will eat them and the crows will eat their food. And you don't want to keep them inside all the time, because otherwise they can't eat and they can't drink, right? So what do? Well, maybe you just let them go outside. Well, no, because then they get eaten. And it illustrates the point that, actually you've got requirements here. You want to be able to isolate things such that chickens can get to the food, but that the fox can't get to the chicken, right? Really, really dumb example, but it's a simple worked example. We need to satisfy these constraints. And in browser land, it looks a little bit like this, right? You think about what you're going to protect from whom. So, for example, your content processes need to not be able to see each other. We talked about the same origin policy a moment ago. Your host system needs to be protected from the stuff that's running in the browser. You shouldn't go to example.com and have your system owned. And the browser profiles, all the secrets that you keep and your cache and all that sort of stuff, wants to be well protected. And you can do this by having various different processes that are isolated, and you set up an inter-process communication mechanism between them, which allows you to sidestep from the unsafe inputs thing, because you've defined the IPC language, yeah? You can sidestep the whole issue of elevated privilege, because only the things that have got access to the important stuff has access to the important stuff, and you manage the rest by, defining the communication between those things, right? Sounds easy. Actually, it's quite hard in practice, and you find lots of things like, we need to find a safe way of accessing this thing because we need to be able to expose this functionality, but there's inherent danger there and all that sort of stuff. So that's basically what's going on here. But it's not the only way to do it, okay? Remember, you've got your rule of 3, unsafe inputs, untrusted language, and high privilege. You can meet your rule of 2 by getting rid of another thing. And, going back to the Firefox versus Chromium thing, the Mozilla approach was, let's make an alternative to the unsafe languages. Let's say, this code has got to be secure, let's not use C++ anymore because friends don't let friends use C++. Okay, so Mozilla started sponsoring the Rust project, and now, practically everyone's using it for their system stuff, unless they want their stuff to get hacked. One of the really nice things, and this is one of the takeaways I want you to have from this talk, is that actually you win in ways that you don't expect, right? The thing that managed to get Rust code into the mainstream code base in Mozilla was not security. It was with the introduction of Firefox 57, there was a load of the styling engine came from their experimental browser called Servo. That was ported from Servo into Firefox. And that was written in Rust. And the thing that allowed the browser engineers to do was to have the layout engine working in a parallel way rather than sequential, which meant that loads of stuff could happen at the same time that previously used to take a long time. So the thing that made Firefox a huge amount safer around Firefox 57 was a performance thing with security benefits and not the other way around. So the lesson there, what can it teach you about secure design? Look for aligned incentives. Find the people that can help you in your quest to make a system more secure and help to push those aligned incentives. So I talked about WASM and JS already. Did you know you can build your native code to run in a WASM runtime? Probably do. You might have used things like ASM.js and that sort of stuff before. You might have used the Clang targets that will target a WASM backend, that sort of stuff. Turns out you can build the vulnerable bits of your browser to run inside that environment as well. So one of the experimental things that happened a while back was engineers started building unsafe codecs and stuff such that they ran inside the WASM runtime within the browser. RLBox was an experimental thing that they did at Mozilla for a while before they realized that actually probably just rewriting the Rust was a more performant way to go. An example of this sort of thing working really well, does anyone remember the WebP vulnerabilities that happened about a year ago, maybe 6 months, something like that? Yeah? I remember this at the time. It was quite funny for 2 reasons. The first was that it's one of these cases where the browser vendors all share the code, and despite the fact that they don't have the same code base, they all end up with the same vulnerability, because they were all using the same WebRTC code, right? The other thing that really amused me is that literally if you went onto the Mozilla Developer Network, which is what Google and Mozilla use for documentation, the example on compiling C modules to WebAssembly was WebP. Isn't that brilliant? Delicious irony, right? And so had they been running this within that safe runtime, they wouldn't have been vulnerable to that particular flaw, but they didn't, so they were. But there's an example that they'd already got on how to do that, which I thought was just great. Okay. So that's a little bit about browsers. Talk a little bit about Chromium, talk a little bit about Firefox. Where else do you use browser tech? Anyone use Slack? Yeah? Does anyone use GitHub Desktop? Anyone use Microsoft Teams? Anyone use VS Code? Yeah? What are all these things based on? What's the common theme here? Electron, okay. So, thinking about that WebP thing, I did a bit of research around the time that happened, because the browsers sort their stuff, pretty well. These days, when there's a 0-day reported in a browser, you can expect the team to have a fix for it in a few hours. The Pwn2Own stuff last week, the Firefox team had a fix out in 4 hours, which I thought was pretty hot. Okay. When the libwebp thing happened, this is what Electron versions and corresponding Chromium versions, the stuff that was running just on my Mac, were. So I think only one of the Electron apps I had on my machine was not vulnerable to that flaw. Okay. And one of the issues with Electron is that you get all of the attack surface of a browser maintained by people that don't understand that. Yeah. So my advice is if you've ever got the opportunity, you've ever got the choice between using the browser version of something and using the Electron version, run like the wind away from the Electron version. Okay. So there we go. That's what we learned. We learned that it's possible to fix big problems because, like, web security didn't exist until after JavaScript, which is a terrifying sentence. We've learned that boundaries are good, but you've got to put them in the right places. I can't remember what we've learned. Oh yeah, incremental changes add up over time. Language choice matters. If you're writing code that needs to be secure, please, for the love of all things good, do not use C++ or C. Okay? Look for aligned incentives. Other people can help you reach your goals. And don't trust people that ship browsers and don't put in the work to keep them secure. Thank you very much.